So we're going to add to all of the alkaniness of the carbon chains that we were discussing in our previous lesson, and we will look at something called a structural isomer. I love this topic because we get so many fun words out of it. A structural isomer are compounds that have the same formula, in other words, the same number of atoms, but due to the way they're arranged, they're actually different compounds. So we take the same starting materials and arrange them differently, and we get different results. So we'll start with smaller things, and they don't have that many different arrangements. But the bigger they get, the more different arrangements you can get. Just like if you think you buy a really small Lego set, how many different things can you make out of them? Not that many. But if you buy a really, really big box of Lego, you can make a lot of different things out of that box. And so that's the same way with molecules. And so we'll start with something pretty small, and that's butane. So, memories from last class, how many carbons does a butane have?
4.
Yeah, it's 4 carbons. How many hydrogens should it have? Well, that's harder to count. So let's draw the first very simple butane first. So we'll draw straight butane. C, 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 and then another C. And we're going to put every other hydrogen around it. So hydrogen, 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 hydrogen. So many hydrogens. How many was that? It's point. 1, 2, 3, 4, 5, 5, 6, 7, 8, 9, 10. 10 hydrogens all the way around. Now, remember, I don't actually write the hydrogens on there because I'm lazy. So we don't write them in. Draw. That's H10. So we have, let me just clean that up there. There. So there's 4 carbons and 10 hydrogens. There's a different way to arrange the same number of carbons and the same number of hydrogens. I'll just go through this to show you because you probably haven't thought about this before. If I put them this way, I now have 4 carbons, but I've made a little branch in the middle. And if I put the hydrogens around, they should still add up to 10. Do they add up to 10? Let's do the count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think I got 10. So I get 3 here, 3 here, 3 here, 1. That's 10. So the name for the first one is boring. It's butane. There's nothing else. There's no numbers. There's no groups. It's just a single chain of butane. Very boring. But the second one requires a little bit more careful naming because it doesn't have a 4-parent chain. What's the longest parent chain with this one? It's a 3. So what name should it have? What's the name for 3 carbons in a row? It's propane. So this is going to be a propane molecule. That's my, let me see if I can draw that. That's this piece of it. That's the propane molecule part. And then I have this other piece over here. This is the piece stuck to it. What's the name of this piece? It's a methyl group. So a 1 carbon is a methyl group. So this is simply methyl propane. Now, a lot of you are telling me it's 2-methyl propane, which is true, but there can't be anywhere else it could go. So if we look on here, if I moved it to here, it just becomes regular butane. If I move it to here, it just becomes regular butane. So if I say something's methyl propane, there's only one place that methyl group can go. And so often those 2's are left blank. So it is a good practice. It's not wrong to call it 2-methyl propane. But if you left it off, it also wouldn't be wrong because there's no ambiguity to it at all. Does that kind of make sense where it's like there's no other thing it could be, so we don't need to be specific sometimes? And when we get bigger, what's our count for pentane, which is a, whoops, as I write 5 first, no, it's C5. How many H's does a pentane have? I think it's 12 as well. So I'm just going to write 12 down here, and we can double check. Now, for simplicity here, I'm not going to draw all the hydrogens. I'm just going to draw the carbons and how they're arranged. because otherwise it's just crowded. So we're just going to draw the carbons in their arrangement, just for ease. C, 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 C. So, yeah, I warned you there's 3 of these. So that's how much space you should give up for this particular part. There's 3 diagrams. So this one's boring, regular, pentane. Oops, pentane. The next one, we're going to start with the parent chain one lower. It's a good way to start with it. Well, it's like 5 is full. Let's go, how many different ways can I make a 4? So let's do a 4 chain. C with a C, with a C, with a C. And I got to stick 1 more carbon on here for this to be true. Can I put it on carbon 1? No. If I put it on carbon 1, it just becomes pentane again. So I've got to start looking at carbon 2. So I've got to start here. So that's my second isomer. So this is a different compound than the first one, but it still has 5 carbons and 12 hydrogens. What's the name of this lovely thing? 2-methylbutane, but we can call it just methylbutane. Right? Just methylbutane, because it can only go on the 2. Could it go somewhere else?
No. On 3.
It could go on the 3, but 3-methylbutane is 2-methylbutane because you would just number from the other side. It's important to consider that. That's a good question. So if I put it, let me point here. If I put it over here, it's the same as if I just flipped this thing over. It wouldn't change the nature of that molecule. Now we have another idea. So we've used up all of the butane molecules. Let's try a propane molecule. So we're going to put a propane molecule here. And now I'm 2 carbons short. Where shall I put it? I got to put one on the middle. And I got to put the other one on the middle. So this is the only other arrangement we can get. So you're going to try these things, and you're going to end up drawing things that actually end up being the same, because they just would spin around to be the same thing. So this can't be spun around to any of the other ones, right? I can't wiggle the chains around and have something else, because the where the connections are different. So this one's fun. So what's my longest chain is still this propane part, right? So we got a longest chain, which is propane. And then I have these other 2 things. I've got something there and there. How do I deal with 2 of the same group? Yes, we use those prefixes of di or tri or whatever it happens to be. So this is going to be di, and then the groups are methyls. So 2 methyl groups is called dimethylpropane. So dimethyl, and I'll just do a quick underline here, because there's 2 of them, dimethylpropane. That matches the red stuff that I have here. So it's important to keep track. Should I need to put numbers on here?
No.
You can probably skip the numbers because they are extra. I can't put 2 methyls on a propane anywhere except for the middle. Then they would become something else. So there's no ambiguity here. The reason for the numbers is to be specific if there was choices. Now, if I was to put numbers on there, what would the numbers be and still be true?
2,2-dimethyl.
It would be 2,2-dimethyl for one's on 2 and the other one's on 2. Both of them are on the same part of the parent chain. So if I was to put numbers on this one, it would be 2,2, and that would be still correct. With my hexane isomers. How many carbons does hexane have? 6. Oops, I don't want red. That won't look as good. Undo. C6. How many H's does a 14? It is 14. All right. So before I count and before I draw, I want to point out something. Look at the pattern of H's. How does the pattern change? Goes up by 2 each time, right? Because if we think about adding a carbon in the middle of the chain, we add 2 every time. So as you go up by 1 carbon, you add 2 hydrogens every time you're in a chain. And so really, we can do this 2n plus 2 guess to figure out what the number of hydrogens are on a big long chain. So if I had like a decane, I could figure out how many hydrogens it would have. It would have 10 times 2 plus 2. It would have 22 hydrogens on it. And so we can do that math without drawing a giant molecule. Okay, let's draw them. I'm going to get sneaky here, and I'm going to draw the first hexane vertically to save me some space. C, 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 C. That's not enough. One more. So that's all the C's in a vertical one. That's regular hexane. I did that to save me some drawing space. So we're going to break it down to the next biggest parent chain, a pentane. And there are two different options for this pentane. So I'm going to draw a pentane as best I can here. And I'm going to draw another pentane lower before I draw my extra molecules on. So those are my two pentanes. And so I'm one carbon short, so I'm looking to put methyl groups on there. What are my choices for putting methyl groups on there? I could put methyl groups starting on where? I could put it on 2, right? That's fine. That would give me a molecule that's different. I now have a different molecule there. What about the second option? Where else can I put it? I can put it right in the middle. That's a different molecule. What happens if I put it on 4? It's the same as 2. Good. Good. That's the point. So if I put it on 4, it's the same as 2. So we can quickly name these. We're getting really good at these names now, right? What's the name of the top one? It's 2-methyl pentane. And this is 3-methyl pentane. And these numbers are necessary because they tell you the difference between those two. So there's 2-methylpentane and 3-methylpentane. We're going to do the next ones here. We're going to do butane chains. So I have 2 drawn here. I think there's just 2. 1, 2, 3, 4. And 1, 2, 3, 4. All right. So I got to put, I'm 2 short, so I need 2 different methyl groups. Where can I put my 2 different methyl groups? I could put them both on 2. That works. That's interesting. It's got a nice shape there. Where else can I put them? If I put them both on 3, does that help? No, that's another of the same thing. That's just a flip of the starting point. Simon?
2 on the second, like down.
Oh, I could put I could put an ethyl group down here, right? I could put 2 carbons down here. That won't work. If I put 2 carbons down here, now don't draw this. Stop. Don't draw this. I'm going to draw this quickly just to show why it's a good idea to check but not actually do. This isn't an answer. So what happens if I draw this? That's the same as something we got before though, right? What else? What is it the same as? It's the same as this 3-methylpentane, right? I have this chain with 1 in the middle. So this isn't the correct answer. So let me erase this. Erase these. How can I add carbons that will make it different, Jaden? Carbon 1 won't help us because that'll just turn it into hexane, right? That just extends the chain. Whenever we put it on the beginning, that just makes the chain bigger. So we got to start at 2. Maya. Is correct. So we got to put 1 here on the 2 and 1 on 3. That's the other option. So we still have a butane chain, and one of the methyls is on 2, and one of the methyls is on 3. It doesn't matter which way we number it because it's 2 and 3 on each side. Yes?
Can you have a group of 4?
You can have a group of 4, but that won't help us here. You would only have a group of 4 if you had a parent chain that was much bigger. You would need a huge chain before a group of 4 won't just make the chain longer. So you would have to have like a hexane and then put a butane off of like 3, and then that would work. Actually, I think that might just change the path. And you would end up with a longer chain and a group of 2. So you'd have to draw that to see how it would work. You can have butyl groups, but they would be coming off of very big chains. So it's true, but unlikely. You would get it'd get huge. So it's true, but unlikely, uncommon. Not unlikely, uncommon. We'll call it that. All right, names of this lovely thing. What's the name of the top one? 2,2-dimethylbutane. 2,2, comma, dimethylbutane. In other words, I have my butane chain and 2 methyl groups, both of them on carbon number 2. And almost the same name, but only a number change. This is 2,3-dimethylbutane. So I've got my parent of 4 butane and 2 methyl groups, one on 2, the other on 3. So that's the other way of writing these 2 different things. So this is when the numbers start getting out of hand. I will not demonstrate the bigger ones. You can do them, but you will get like huge numbers of isomers if you do more of those. I will ask you to generate isomers, but I won't necessarily ask you to generate all the isomers. Just another isomer of this, another isomer of that. Not, hey, this is an octane, show me all the isomers. That would get out of hand. It would be huge. It'd be like, draw me 2 extra isomers of this, and it's easy to rearrange, and so on. Alkanes are also awesome because they can make loops of themselves. So you can connect an alkane in a circle, and it's called a cycloalkane. So we have this cyclo prefix that we add to things, and it works all the way. So it's long enough to loop around and get ringed to itself. So we're going to draw a few of these, and it follows essentially the same rules. We're just adding the concept of a cyclo first. So cyclo is added to the regular prefix counting the number of carbons in the loop. So we're going to first do the same way we do all the other ones. We start at the end. We start at the back and work our way front in the drawing. So what we're going to do is my baseline here will be the cyclopentane. How many carbons do I have? A 5. So I'm going to draw a 5 loop of carbons. So I will draw it simply a C with a C with a C with a C with a C. I can connect them all like this. So I've got a circle of 5 carbons. And then I have my other group here. I think I'm going to just put it here. I have my ethyl group. How many carbons are in an ethyl group? 2 carbons in an ethyl group. So I'll just pull it from somewhere easy. There, carbon, there, carbon. So that is my ethyl cyclopentane. Does it matter where in the circle I draw my ethyl attached to? No, it's all the same. It doesn't matter where it is, it doesn't change. If I had 2 different groups off of it, which we'll come to, it will change. You start numbering based on that if you have more than one. So right now it doesn't matter which way you spin this around, it's just an ethyl group stuck to a circle. There's no relation to any other things. When we start doing cycle groups, we start really loving this line notation because it makes life a lot easier, especially for the circles. So I'm also going to draw the line diagram for this. And so that's just going to be your... Oops, that's not the right shape. That's not how a pentagon works. There's a reasonably good pentagon. And we don't draw our lines, our ethyl group, off the side straight. We draw it with a little bit of a bend to it. So we will draw this one out and then up a bit. Because we try to put that bend in it because that's the way the carbon molecules actually look. And it's also easier to count if you're counting number of carbons if they bend back and forth and you're counting number of zigs in the zag. So we're going to slide this up and try to draw cyclooctane. 1, 2, 3, 5 tetramethyl cyclooctane. What a mess. So, octane, octagon, stop sign. Got this. So, draw a stop sign. It's been better. It's an octagon. And so I have my octagon here, and so there's 8 corners on my octagon, and I have 4 methyl groups that I need to attach to it. Now, the good news is that you only need to pick a place to start, and then everything after that just follows from where to start. Now, all of the groups are the same, so it doesn't matter where you start. When you have different functional groups, they will start getting different priorities. So you start numbering based on what each of them are, but we're not there yet. We're still doing all alkyl groups. So the first one is a methyl group, and I'm just going to put it off the side here. There's 1 methyl group stuck off the side. So we'll call that one number 1. So just a little hint, just like that's number 1. Just like there, it's just 1. So I'm going to number, whereas the next one is on number 2. So that'll be 2, 3, 4, 5, 6, 7, and 8. So those are all where the numbers are going to be. So those aren't part of the diagram. They're just me showing you how I'm counting. So where's the next methyl group get attached to? On number 2. Okay, number 2, another methyl group. Where's the next one? On 3, next methyl group. Where's the last one? 5. So I skipped 4. 4 didn't get one, but 5. So this is the way it works. So 3 of them together and a 5. So it's 3 together, skip, and then the next one. That's how we number it. Now we can start the numbering anywhere, but this way of numbering gives us the smallest total number. 1, 2, 3, 5 will be the smallest arrangement of numbers you could get for this shape. So if I could start numbering there, I'd get an 8 in there, it would be bad. So, okay. I got that. Any other questions based on this? This is how I would number it. Okay, hearing nothing, I drew some for you, and we're going to name them. So we're first going to do all of our normal steps here, starting with, we start with the circle here. So how many are in my circle? 5. So what's the name of my circle? Cyclopentane. So we're going to get cyclopentane. Great. Now, what are my things stuck to it? I got that thing and that thing. What are they?
I say they are ethyl.
They are not ethyl. They are methyl groups. So they are single carbon groups, methyl groups. So there's 2 of the same group. So this is a dimethyl group. So this is a dimethyl. So let me rephrase that. It's not a dimethyl group. It's a dimethyl compound. So this whole thing has 2 methyls for 2 methyls. It's not a 2-methyl group. That's wrong. Okay, so dimethyl is what I want to write. So is there a numbering scheme that we need for this? Does it matter where these 2 methyl groups go? If I move them, would it change it? Yes, it would. I could put the 2 methyl groups on different carbons or the same carbon. Are they on the same carbon?
Yeah.
Yes, so it's going to be 2 of the same number. We can choose any number we want. What number should I choose?
1.
Ones. I can choose any number. Well, I want to choose the smallest number that still works. So this is going to be 1, 1 dimethyl cyclopentane. So it's 1 and the same. So it's basically saying 2 methyl groups on the same carbon of a circle of 5. So there's on the same carbon, 2 methyl groups on a circle of 5 carbons. That's what the name fully means out. Look at this ugly thing. It's a real molecule. How am I going to name this? How many circles do I have? 2 circles. So which circle is the parent? The bigger one. Excellent guess. So this one has 6. This one has 4. So the 6-1 is the parent. So that's my base. So my base in this case is cyclohexane. So cyclohexane. And then I have to name my group of 4. What is the group of 4 name? It's butyl, right? It's a butane group. So it's a butyl group. So it's a cyclobutyl group. So this is a, whoops, slid it all around there. Let me slide it back to where it's supposed to see it. There. Cyclobutyl. Oh, I spaced it right. Good. So cyclobutyl cyclohexane. Yeah, they sound terrible when you say them out loud. But when you read them, you can figure out their structures, which is the goal of these names.